I don't know if there's someone to say, or should I just go?
Do you want me to say it for you?
No, there's time. Usually there's someone in back to kind of like, it's good.
I think Tom's going to do that.
Yeah. Good? Should I go? Okay, great. All right, so it's the last lecture. And I'm painfully aware that I'm the last thing between you and the weekend. So again, I've had a really good time with all this. It's been fun. There's a lot that I would still like to try to get through, and I don't think it's all going to happen. I'm going to come back to this slide a few times. It's one thing. It's sort of a thumbnail of a lot of stuff that once you understand it is like a nice reminder of what's going on, like a cheat sheet kind of thing. So I'll come back to it. And so, but my goal is to be able to explain what's on this slide today. Okay. So we're going to get to that, but first I'm going to back up a little bit to where we ended last time. Okay. So if you remember last time we were talking about, we have a lot of statistical procedures when someone gives you a statistical model, but then I was talking a little bit about like a kind of general purpose statistical model for the LHC. And so that, if I go back here, I think this is pretty much where we ended last time. I was thinking if I actually have distributions, so we had this plot right here, that was for some observable x, and we were imagining this, hypothetical example at 750, and the data, happening here so this curve right here is f of x given what do I call it, alpha there, okay, so you have n observations and n data points that are happening at different points along here. Usually you display it like this. So that's what the n is. You have a Poisson probability that you observe that many events given some expectation nu, and then this is the shape information. And the idea here with alpha those are the parameters of the theory that you're testing, and those parameters might tell you both about the number of events that you expect, the normalization, as well as the shape. And when you have common dependence, alpha appears in both of those places, then you can have some tension in the fit between the number of events and the shape information. Okay, and then we just took the same idea and repeated it many times, like when you have, it's like, this would be some other channel, like we talked about, for instance, in that example, Higgs to 4 leptons or something like that. You just have an extra channel or category of events, and you just have a product of a bunch of these. And then we talked about different special cases. And one of the special cases when we just consider number counting. So you might have a signal region with some number of background events that are expected, some number of signal events expected. And then this is the number that I observe in my signal region. I might also have a control region that I use to try to estimate the background. And that will work if I can relate this nu b, the number of expected events in that background control region, to the number of events in my signal region via some factor tau, okay, which is known in this case. So this is a very common situation. So, and when you treat it this way, simultaneously, the control region and the signal region, what's nice is you can propagate the uncertainty about the background in a very natural way. So you think of nu b as just some free parameter of the model. I don't know what the true background is. It's just some parameter, but I have a joint or simultaneous likelihood about the two different pieces, and based on my observation in the control region, I'll know something about what's going on with the background, the unknown background rate. Okay, tau is some factor that tells you how many background events you expect in your control region compared to your signal region. So the example that we gave, one of the ones that we did was if you thought of it as a sideband. the ratio of this area to the area there is tau. Okay, and so in that situation, in something like this, you would be trusting your theory or your Monte Carlo to tell you about the shape, because tau is an extrapolation factor, but you wouldn't be relying on the total cross section, okay, or the efficiency of your electron identification or things like that. But you would be relying on the Monte Carlo to tell you the shape, okay, and then you can get into other things. Okay, well, what if I have uncertainty in the extrapolation factor, and you just kind of keep doing things like this. Here it doesn't matter. Any kind of relationship, as long as you can find some set of events where you can measure and you can relate through some, it doesn't have to look like this. It any kind of likelihood term, where nu b in this example would be related to nu b there through some functional relationship. As long as you can do it, it will work.
If the control region is on both sides, then you're in some ways happier about extrapolating inwards, right? So is there a way to take it?
No. I mean, this is kind of a leading example because it's got a particular shape. But this is like the formalism is kind of super duper generic. So it might not have anything to do with sidebands. It could be something like I gave this example of if you have backgrounds that come from, say, jets faking leptons or something like that, then you might be able to make an argument about them not showing up in certain charge combinations or flavor combinations. So it can not look like that, but it is true that as a physicist, you're going to trust something like this more than some more complicated type of extrapolation. And so that's one thing that I skipped a whole section I have about whatever this, I called it the scientific narrative, which is basically, you tell a story about how you do your analysis and how you understand all the different pieces, and at some point you have to convert that story into your likelihood function, and the more convincing that story is, the more everyone's going to believe what's going on, right? And so there's a translation from that story to equations, and so people at the LHC experimentalists love data-driven things, and they're a little bit like, overly excited about data-driven background because they say, oh well, I don't have to trust the Monte Carlo and all these things, but of course, when you do that, you're making all sorts of other assumptions about how you can relate these control regions to your signal region, and they may or may not be, valid statements. So, like, I make this joke that I could use the temperature of the LHC to estimate my background. That's data driven, right? But the extrapolation is not very trustworthy, right? And there are a lot of data-driven backgrounds that have a lot of problems with them, but I don't want to get into all that. That's a whole lecture. Okay, so then there's this next point, which is I just wanted to show this, and then I'll move on from this. Is that what if I wanted to think about something like maybe you shouldn't read this yet, but if I wanted to think about an experimental thing like the calibration of my calorimeter or something like that. That's some parameter that I can change, the calibration constant or something. It's going to change all my distributions. It has some uncertainty. I need to incorporate that uncertainty into my likelihood, right? So how do I know that the calibration of my detector? Well, I made some other kind of calibration measurement usually, right? Like I had the Z-peak, and I looked at the E plus E minus, and I made sure that it, sat at the right spot, right? So there was some measurement that happened, and there's a whole team of people that did that measurement, and that measurement might be pretty complicated, right? But in principle, I could use the same kind of formula to describe that Z-peak measurement, and now one of those parameters is just like the calibration of my calorimeter or something like that. Now, it's not really practical that you take all of these very complicated measurements and keep including them in this, because the likelihood just would get way too complicated. So, and oftentimes those measurements, in the end, you measure the calibration very well. You have like a 1% uncertainty or something on it, right? So what happens is that if I think about, so let's say that this particular alpha parameter that I'm thinking about is like the calibration coefficient for my calorimeter. There was some very complicated experiment that the people that are experts in the calorimeter did to try to calibrate the the detector, they have a likelihood function for it, and they say like, okay, this is my best calibration for the calorimeter. Okay, they have some uncertainty on it, and they have this whole likelihood curve, which might have resulted from something very complicated, like a formula like that. But in the end, it pretty much looks like a parabola or like a Gaussian or something, right? So I don't need to communicate all of that complicated stuff. I can just say, well, this thing is approximately, looks this likelihood curve basically just looks like, looks like alpha minus, alpha hat, squared over some uncertainty, sigma squared, right? Something like that. And, this log likelihood is basically just a Gaussian, right? So what happens is that you can replace a whole big hunk of this that might have been a complicated measurement with just a simple Gaussian or something like that. And that's what we do all the time is we have a likelihood that's complicated, and then we add additional terms that we call constraint terms. Constraint is maybe a bad word because it's not like a delta function constraint. It's just an extra little piece that's usually like a Gaussian or a Poisson, some idealized version of a more complicated measurement. Okay. The part of the reason that I mentioned that piece is that that's the place where you make that Bayesian flip very easily. Okay. People often think, what's my uncertainty on the calibration? It's like I know the calibration constant, and I have a 1% uncertainty, and you think of it as a Bayesian in a Bayesian way, as like what's the distribution of the uncertain parameter. And in this way of writing it, you're a little bit more careful to say, alpha is my uncertain parameter, and this A is basically the result of the measurement that I did, this other measurement that happened. Okay, so if you want this AP is basically that's what I mean here. Okay, so I can call that alpha P or AP, which is basically the same as the best fit value that I got from that previous measurement. Okay, and now part of the reason I'm spending some time on this is that this is not the way that people usually did it. Usually the way people did it until LHC is if you had uncertainties on some on calibration constants or background uncertainties. When you generate a bunch of, say, toy Monte Carlo, you would randomize the parameters of the background or something like that. But when you randomize a parameter, Monte Carlo is integral, right? So you're doing an integral over a parameter, and that's only possible in a Bayesian way. Okay, so this way of writing it is like this sort of more careful way of doing it where you're not making this Bayesian mistake. And when you do it, one of the things is that when you generate your toy Monte Carlos or something, you have to randomize this number, which is basically imagining that you redid the calibration measurement and you got a different answer. And this gets a little bit funny because I could consider things like the mass of the top quark. I don't know the mass of the top quark perfectly, right? I need to include it in all my background simulations. I have some uncertainty for the mass of the top quark, and if you really wanted to do it in a hardcore way, I would need to imagine redoing the top quark measurement and getting a slightly different value and redo, so it becomes kind of hard. So this AP right here is basically summarizing the results of all of these previous measurements, and you need to imagine those things as the random things, because those are what you observe. Okay, the true top quark mass is not random; it's just some unknown parameter. Okay.
What would be the wrong thing to do? What's the
mistake? So the wrong thing is that if we agree, if this thing is something simple, like I'm just going to so in this scenario right here, this log likelihood is equivalent to what in that notation, AP given alpha p is equal to like a Gaussian for the quantity AP given alpha p and some uncertainty, sigma. Okay. So what you're saying is that if I knew what the true value of like the top quark mass was, or my calibration constant or something, the measured value is going to be random, and it's going to be centered around the true value, right? I actually made one particular measurement to measure the top quark mass, right? So AP takes on a specific value from that observation, and then I have a likelihood function as a function of the parameter, the top mass parameter, and that's what this curve is. Okay, and this might have resulted from, the real thing might have been more complicated, but we're saying I think I can it's approximately like a Gaussian. Okay, and this is convenient to work with. What people would usually have done is say, because these things have like the same units and they sit in the same space and everything, it's very easy to confuse the top quark mass parameter with the observed, like the maximum likelihood estimator of the top quark mass, right? And so what people would often do is say, oh, I know, they would think of the probability of alpha p given AP. They would think, I made my measurement and I know the top quark mass within whatever percent, with some uncertainty. And they would think of it as in a Bayesian way as the top quark mass has a distribution associated to it. And that's what I'm writing here. So this is how people usually think of it. It's really the measurement that you made, the likelihood times some implicit prior that was never mentioned, which is that hidden one usually, that some uniform prior that you didn't realize is there. But we can forget about that, latch on to the likelihood piece and stick it into the likelihood and be careful. But when we do that, when we generate toys, we need to randomize something, and we don't randomize the top quark mass parameter. We randomize the maximum likelihood estimate of the top quark mass parameter. So we need to imagine that we redid the experiment. We got a slightly different value for the top quark mass. So this is it's very subtle, and I don't want to spend too much time on it. But this was like from the LEP and Tevatron time. Everyone always did it kind of this way. This is what happens when you include uncertainties by randomizing the value of the unknown parameter. Okay, and this way is like the kind of more careful, frequentist way of doing it. But both Bayesians and frequentists would agree that this was the actual likelihood. So, and I had a slide that I got rid of like, does it matter? And the answer is that if you're trying to do 5 sigma and you have, order 10% uncertainties, it can make a big difference. Like 5 sigma can really be 4 sigma, and you're just fooling yourself. So, it does make a difference. Okay, but I don't want to belabor that point too much. But okay. So this, I'm not going to show too much here. I just wanted to show that these slides are old, but when we were doing the Higgs analyses, we had like all the different ways the Higgs could decay, all the ways the W's and Z's could decay. Then we broke up the events into all sorts of different categories depending on the lepton flavors, the number of jets, all this kind of stuff. And this formula is, the same template formula is what we used for the Higgs discovery. And at some point before, this was in kind of like, December-ish or something, 2011, this is sort of like what the likelihood looked like in some way, okay, that I'm not going to bother describing, but they got very complicated, and it's a cool picture. So I just wanted to show that. And this also just shows, like, as a function of time, how many different data sets or like categories of events we were combining, the number of like modeling components, like histograms and things like that were involved, and the number of parameters and the likelihood. And you see it was just like growing exponentially. And now these things are way up here. The number of parameters is in the thousands, and they've gotten very, very big and complicated. So, what you're doing is you're just like I drew these plots here. These are the kinds of plots that you're talking about. So, the only reason I'm showing you this is that this formula that I'm talking about is that you didn't have to generalize it to do the Higgs discovery. This is exactly that formula is what was used for the Higgs and basically all of the LHC results that are coming out for searches and things like that. You can think of in that way. Okay. All right. So that was the end point that I wanted to say about modeling. If people have questions, ask. But otherwise, I'm going to keep going. So now I'm going to remind you quickly what we did last time about hypothesis testing, because again, I want to get into this picture and something more general. So maybe I'll just do this again. These kinds of plots you see all the time from the LHC. There's sort of roughly 3 types of plots. One, in this case, it's like the unknown mass of the particle. This is sort of a plot that's saying like the quote signal strength or something. So 0 means there's no signal. Negative means there was like a deficit of events compared to what was expected. Something positive means there's an excess of events. This plot turns into the p-value, or basically the significance of the bump as a function of the mass. And then the top plot is the limit plot, the upper limit on the cross-section as a function of the mass, right? So these are like the kind of typical sets of plots you see in a lot of searches. Sometimes it's not a one-dimensional one. It's a 2-dimensional scan for like, the masses of the chargino and gluino or something like that. And then so it's harder to look at, but it's the same sort of class of plots that we're going to make. So when we talk about discovery, it's this plot, okay? And so the simplest picture that we started with is you just count events, right? And so what I want to focus on is this axis, okay? This axis is the quantity that you're using that you're going to end up like, you're going to see this and you're going to integrate out here to calculate a p-value, right? And that's what, if that thing is really small, you're going to claim a discovery, right? So so what I want to focus on is this axis. This number of events observed works if you're just counting events, right? But what do you do when you're doing something much more complicated, like what I just showed with the Higgs with all these different channels and things? It's not counting events. There's shapes and all sorts of information, right? So we also talked about the Nyman-Pearson lemma, right, which said that when your data is more complicated, the best possible way to sort of decide to accept or reject your null, like claim a discovery or not, is based on the likelihood ratio, okay, which was previously in the middle of that, right? So, and that works no matter how complicated your data is, okay? So the thing that I'm trying to get back is that what we're going to do is we're going to take number of events observed and generalize that, and we're going to replace this axis with the likelihood ratio. And that thing is going to be, it's still just a real number that characterizes the entire experiment. And that's what we need. If we're going to calculate a p-value or a tail probability, we need one variable, a singular scalar variable that we can integrate to get a p-value. And that thing in general is called a test statistic, okay? And so here's my kind of more general picture of it, is I'm just going to have some quantity, some real valued quantity, t, okay, which is a test statistic, which is going to, when I do my experiment, it's a map from the space of my data to the real line, okay? And as long as I can come up with a map, there's lots of possible choices. As long as I can get a real valued number like that, I can then think about what does the distribution of this quantity t look like under my null hypothesis, right? And then I can still do the same thing where I kind of find some critical value where the tail probability here is whatever my 5 sigma requirement is. And if my data falls in here, I claim a discovery. And if it falls over here, I don't claim a discovery, right? Or equivalently, I get an observed value of this t, and I do the tail integral, and I get a p-value, right? And if this p-value is smaller than some threshold, I claim discovery. Like totally equivalent statements.
What do you do for distributions that are bound?
You mean like if it doesn't go off to infinity?
Yeah, the parameter that you're using.
Yeah, so this is not a parameter. This is an observed quantity, right? I get the data. I have some complicated function that I evaluate, and that's what t is. So t is a function of the data. All right, so let me go back a little bit. Is it when so this t is playing the same kind of role conceptually as number of events observed, right? And so the distribution of this thing is going to depend on your theory, and that might depend on phases or whatever parameters, right? But this is an observable quantity, and so the number of events is like the simplest kind of test statistic you can think of. The more kind of general purpose one that we're going to have, okay, I unfortunately deleted this part, is a likelihood ratio. Okay, so I'll just write it again. So if I have I can have a particular kind of t of x that looks like the probability of x given my null over the probability of x given my alternate, right? And this thing, if these are totally fixed, quantities, then it's a function of x, and it takes you to the real line, right? And that was what we did when we did this this proof, right? And it fits into a picture like this. Okay. So now the thing that I want to get at here, I'm going kind of slow, is that I want to now think about uncertainties, okay? If I have uncertainties that change the distribution, what happens, right? Well, let's imagine I keep this t quantity fixed, okay? If it's fixed, but my theory is now a function of some parameters alpha, then as I change alpha, different values of alpha, the distribution of the data looks different, right? So when I evaluate t, I'm going to get a different distribution for t, right? So now for all those different values of alpha, I'm going to have basically a different p-value for the same observation, right? So now you need to think a little bit, what is my requirement going to be for discovery? Before it was if the p-value was less than some critical number, then I'm going to claim discovery. But now I have a bunch of p-values for all the different values of the parameter, right? So when would I like reject my null hypothesis? If what?
P is the most economical.
Yeah, exactly. So that would be the nicest thing, is that if you would reject this thing, if you can find any value of alpha where the p-value is acceptable, then you're just saying, okay, well, there's some value of my the parameters that describe my uncertainty, if my calibration was this, then the p-value is big, no problem, right? You're not going to want to reject the standard model if you can find some value of your calibration constant that describes the data, right? But if you can't find any value of the calibration constant, that describes the data, so if the p is small for all values of alpha, then you're going to reject. So exactly. So that's the kind of logic. But then the hard part, of course, is that now I have to calculate p-values for all different values of alpha, which is going to be a big pain in the butt, right? Okay. So I'm going to go back here, and I'm going to change, instead of having two discrete hypotheses, I'm going to think of sort of alpha naught and alpha 1, and these can be parameters. Okay. So what happens is that if I could somehow find a t. Okay. Now see if you can follow this logic. If I can find a t, a particular map of the data where the distribution is always the same, which seems hard, but if I can magically find a function where the distribution of t is independent of the value of alpha, then life is going to be easy again, right? Because I just calculate p of alpha once, and it's the same for all of them, and life will be easy. So there is a way to do that, and that's what's called the profile likelihood ratio. Okay. So in this setting, it still looks like a likelihood ratio. Okay. You have a likelihood in the numerator and a likelihood in the denominator. This is it if you thought of it as the probability density of some data. Okay, this is in the notation I had. This was like the observed data, like these events and things like this. And then the G was the set of things that look like these A's. Okay, but it doesn't really matter. This is just the data. Okay, and these are the parameters. But the data is fixed, right? So if I fix the data, I've got the likelihood function that depends. And what I did here is I split it into two types of parameters. I have the parameters that I care about, the things that I want to measure. So if you think of mu as like a cross section. That's the thing that I want to know. And then theta are all the other things that I don't care about, like systematic things like calibration constants, unknown background rates, all that kind of stuff that are generically called nuisance parameters. Okay. So this quantity here. In the denominator, what you're doing, the mu hat and theta hat are saying, find me the maximum likelihood estimate of the whole likelihood. Okay, so you scan all the parameters, you find the best fit point, and that's the denominator. Okay, so this is the likelihood under the most favorable conditions. And then in the numerator, you say, I'm going to fix the value of the parameter of interest that I care about. That's the value that I'm testing. Okay, and then I'm going to maximize all the other parameters, keeping that thing fixed. Okay, so this theta hat of mu means find the best values of the nuisance parameters for a fixed value of the parameter of interest. Okay, so if you do that, you can calculate both of these things. It's still a number, right? But it's a function of the parameter of interest mu. Okay, it's not a function of the nuisance parameters. You've quote eliminated the nuisance parameters from that. Okay, and so the thing that's not at all obvious. Before I get that, so here's a graphical version of it. Here's some data. I have a statistical model that's got like some background piece. It's got a piece over here for like a z-peak and another piece for the Higgs. Okay, this is the best fit version of the model. The red part tries to fit the Higgs. The blue part fits the z. This fits some other background. This is the best fit version. Okay, so that's the denominator. And then this one is, say, if I'm testing the background only. My null hypothesis is the background only, then mu, my parameter of interest, is 0. That means like the cross-section is 0, okay? And so now what is the best fit version of this plot with no signal component? It looks like that, okay? And you can tell it's not a very good fit, right? I mean, this black line is not describing these data points, right? So that's the value of the likelihood in the numerator, okay? And basically the likelihood ratio between these two plots is the quantity that you're going to use, okay? That's the test statistic. Called the profile likelihood ratio. Now, why do you care? And the reason is, okay, you don't have to read it, but basically it has that property that I wanted before. The distribution of the profile likelihood ratio is independent of the values of the nuisance parameters. Okay, at least when you collect a lot of data, it's independent of the nuisance parameter. So it's a very nice quantity because it's kind of easy to calculate, and it also has all these great properties about being able to deal with uncertainties. So at the LHC, we're using the profile likelihood ratio basically everywhere for. Let me see if I can find for our searches. So now let me explain this plot. So here mu is the parameter of interest that I'm scanning. Imagine that there are some other parameters like nuisance parameters. What you would have is if God told you the value of all those nuisance parameters, you would have, and they were fixed, you would have a likelihood curve that was pretty steep. But when you profile the nuisance parameters, the likelihood curve gets wider. Okay, and when the likelihood curves get wider, that looks like a bigger uncertainty. So that's good. It's reflecting the fact that there's uncertainty there. So you have a wider value of it. It's a whole curve. This is the best fit point. Okay, so and what you're considering is like what is the change in the log likelihood from this point to some other value of mu that you're considering. So if you're doing hypothesis testing, like for discovery, you're testing the theory that there's no signal, right? Your null hypothesis is no signal. So what you do is you go over here to mu equals 0, and you evaluate that function. You evaluate -2 log of the profile likelihood ratio when mu is 0, because that's your null hypothesis. So the height of this curve right here, that's the value of this t. That's the test statistic, okay? And this green curve then gets mapped into this axis, okay? So you see what I'm doing? I'm taking Q0 here. So it's Q is basically the -2 log likelihood, and 0 is telling me the value of mu that I care about. I'm turning it, that's this axis. And for this particular experiment, the height of this curve is whatever, 6.6.5 or whatever, and that would be the observed value of t when I'm testing the background only, okay? But if I imagine doing the experiment over and over again, the data is going to change, the best fit's going to change, and this curve is going to wobble around, right? Now let's imagine for a second that it's the true scenario is the background only. If the true scenario is the background only, then that means that most of my, if I run a bunch of, toy versions of the experiment, usually there's not going to be a peak there, right? Because there's no, so it's going to fluctuate around 0. So that means the best fit value of mu should be around 0, right? So the curve is going to always, the curve is going to be fluctuating like this. And when I evaluate the curve at 0, the value of this green bar should be pretty small, right? So what does the distribution of the Q0 look like for the background only? It's mainly peaked at 0, and then it's falling off. The chance that you have a fluctuation of the background only with a really big peak that gives you a mu that's way over here is small. And that's why there's a very small chance to get those kinds of things. If you actually have signal there, if you think about the signal plus background, like let's say this, the true signal is over here somewhere, then most of the curves are going to be like this. And when I evaluate the value of this Q0, I'm going to be following the curve way up here, and my values are going to be big. So that's why under the signal plus background hypothesis, it's peaked way over here somewhere. Okay, so you have to kind of think about this curve. Imagine the data changing, the curve changing, and then you can sort of understand these two distributions. And so this is the test statistic that we use for discovery, and this p-value right here is what gives me, the p-value in this curve, okay? And you have to do this over and over again for all the different values of the Higgs mass that you're considering. Okay, so this plot would all be for like a given value of the Higgs mass or whatever particle mass that you're testing. Okay, so I know that there's sort of a lot of like spinning around and pictures and things like that, but that's how we do the Higgs, and the reason that we use this quantity is because this distribution is basically insensitive to all the uncertainties. Okay, so we think that this p-value is a robust quantity, and yeah. Okay, is that fine? Yeah.
Is there a conceptual difference between the double caret and the single caret?
Yeah. So the only difference is that the single hat just means the unconstrained maximum likelihood fit. So like you just do the fit with everything floating, and the double hat means it's a quote conditional maximum likelihood fit. Yeah, because your mu is fixed. Exactly. So in this example plot that I showed back here, one of the mu's is going to be, for instance, describing this, the green background. And you can see here, it's way over the green histogram because it's trying to explain this excess, right? Over here, when you let everything fit, it looks just like the green, histogram underneath because there's no tension in the fit. Everyone's happy, right? So the value of that particular theta, which is describing, this background, is different in the two cases. Yeah.
What happens if you don't have data? Say you have a model and you only have one,
Mm-hmm.
and you want to set some limits. In principle, you could do, and you want the average of,
Like the expected limit?
yeah.
Yeah.
Expected limit. And one thing you can do is you can do many Monte Carlos and then average them.
Right.
But is it also okay to just take the mean? That's the thing.
Yeah, so so that question is, there's a slight difference between the mean and the median in these kinds of cases. So you need to define what you mean by the expected limit, and you can kind of pick one. The mean, will be sensitive to, transformations of your variables and things, and the median's not. But usually they kind of pretty close to each other. But so this one paper that we had, this is what basically the paper that kind of established using the profile likelihood ratio for the LHC. And this is a figure from it, which is exactly what we were just talking about. So it's using the median. So you're imagining here's the signal plus background distribution. You take the median value of that quantity, and then you're looking at the p-value, under the background only, assuming that the data were like the expected version and this median sense of the signal plus background, and then that's how you calculate your expected p-values, and you get all your expected limits and things like that. So this paper had two parts to it. One was basically saying the logic behind the profile likelihood ratio, and the other one was the fact that building those distributions is really expensive, right? Especially if you have something like the LHC and that big, huge likelihood that I showed, you'd have to simulate the whole LHC, fit the two different fits, calculate that quantity, and you get one value of this test statistic, or Q or whatever, and you put it into your histogram, and then you do it again, the whole LHC analysis, right? Fit everything, you get a new value T, do that over and over and over again. You have to do it millions of times to be able to get out here to tail probabilities that are going to be the kind of 5 sigma numbers that you want to get at, right? So numerically, it would be very painful. And in that paper, what we did is the other thing about the profile likelihood that's important is that not only is its distribution independent of the nuisance parameters, it has a known distribution. And if you didn't have boundaries and things, it's just a chi-square distribution. So that's why people use chi-squareds all the time, and that's called Wilkes Theorem. So I think I have all these slides up, but basically, so that's where I'm mentioning Wilkes Theorem. Okay, so let me write it out because it'll be better if I just write it. Is that okay? So the starting point is that I'm going to have minus 2. Oh, I hate that truck. Minus 2 times the log of this profile likelihood ratio, lambda of mu. Okay. So this is just some quantity, right? Now I want to. So that's what's called Q mu, and that's what's called like Q mu in this plot. Okay. But this is a quantity. It's like the axis. And now I need to know what does its distribution look like. Okay, so I have f of this quantity. But to do that, I need to give in something. And I need to tell you what is the true value that's actually generating the data. Right? That doesn't need to be the same value as the one that I'm testing. Does that make sense? So mu could be 0. That means I'm testing the background only. But I could ask, what does that look like when the signal is actually present? Right? So then I can have mu prime here, a different value of mu that's generating the data. And so this distribution is known, and it's in general it's called a non-central chi-square. And this is called Wald's theorem. Okay, and it has a special case that if if mu equals mu prime, whatever, then this distribution is a chi-square distribution. Okay, and the dimensionality of it is with whatever the dimensionality of your parameter of interest is, mu. Okay, and I should also, I guess it would have been good if I would have written comma, what did I call my nuisance parameters, theta or something? So these are the nuisance parameters, and it looks like a chi-square independent of the nuisance parameters. So it's always true, and that's a very non-trivial thing. So and this is called Wilkes Theorem. Okay. So this is why a lot of times people talk about chi-squareds and things like that. The more kind of general, like chi-squareds usually come from assuming everything's Gaussian. But there's a much more powerful general thing that's even when your likelihoods are all these complicated plots like I showed before, if you evaluate -2 log of the profile likelihood ratio, that quantity has a chi-square distribution. Okay, and when these two things are the same, and when it's not, it's a non-central chi-square distribution. And so, and then there are special cases when you have boundaries and things, and that's basically what we work through in this paper. And what this shows is that here we actually generated tons and tons of Monte Carlo experiments and made a plot, histogram, and then we overlaid the prediction. And this is not a fit to the data. That's like 0 parameter prediction, and it fits very well, right? And this is for the signal plus background scenario, the red one. So this is Wald, and this is Wilkes. And because of that, it took, for the Higgs time, we're talking about like millions of CPU hour of Monte Carlo to make those plots, and instead you can turn it into something that you basically do, one fit, and then you can calculate everything very fast. And through that you can do it not just for discovery, but also for all your expected limits and error bands on the limits and everything you need. So once you have those two distributions, you can calculate observed limits, expected limits, error bands on limits, and all of that kind of stuff. So this paper is, kind of whatever is used for the bulk of the LHC analyses now. Okay. So I haven't really talked about the top part, which is has a lot in common. The difference here is that maybe I should just pause for a little bit because I know this is getting very dense. Right? Okay. So this quantity again, this could be anything, but let's think of it again as just like the cross section for some new particle. Okay. 0 means there is no new particle, and then there's all sorts of other things. When I do an upper limit, right, like this plot right here, let's just pick a mass. So we don't, the mass is just pick a mass, and I want to know what's the upper limit, for that mass, right? This vertical axis is the cross section, right? So that's the same as this axis here is the vertical axis in this plot. Okay, and so what I'm asking is how big could the cross section be before it's inconsistent with the data, right? So here you see that the data, the best fit, given this data set, the best fit value of mu is right here. So you could think of it as like whatever 1.7 events or something like that, right? Once you get to in this picture, like at some other point over here 5 events, I would ask is that consistent with this observation? And to do that, or let me use this example, the 3.5 events. If I want to ask is 3.5 events consistent with this observation, what do? That's the value that I'm going to be testing. I evaluate the height of this log likelihood ratio at that point. So that's this Q mu here for the particular value that I'm testing, and that turns into this axis right here. So see Q mu and Q mu, right? Okay, and now if this was true, now we have to do the same logic we did before, but the plots are they're going to switch roles. So if the signal plus background is true for this particular value of the signal strength, 3.5, then these curves are going to mainly sit around here. And the height of this Q mu is going to be small usually, right? Because the parabola doesn't have far to go, right? So under the signal plus background, it looks like some falling distribution, okay? So that's basically saying if mu is 3.5 that I'm testing, and the true value of mu is also 3.5, I expect it to be a small number, and I'm in the Wilkes Theorem case, I expect it to look like a chi-square distribution, so I expect it to be falling, steeply, okay? And then, but if here, but if the true thing is background, then the curves would expect to be over here. And when I imagine the curve up here, it's going to have a big value of Q mu, right? So now the background only is the thing that's pushed out. And this bump over here is now, I'm testing mu equals 3.5, but the true value is mu equals 0. And so I have this Wald's theorem non-central chi-square, and that's what this blob is over there, okay? And so once you do that, you can still calculate p-values. And then basically what you do is you just scan this mu until that p-value is 5%. And so whatever value of mu makes that thing be 5% would be your 95% upper limit. Okay? And so that's what's happening here. For a fixed value of the mass, you're scanning mu. As you're going up, you're scanning mu test. You're remaking that plot over and over again until the p-value hits 5%, and then that's what makes the solid black line. Okay, and that way of doing it, what's nice, again, it is including the systematics and all the uncertainties. It totally scales to, this profile likelihood ratio I can calculate no matter how complicated the likelihood looks like. It's just a number, right? And so it works for those really big, complicated likelihoods that I was showing. So it takes this very complicated data and just maps it into, the real line in a specific way that has all these nice properties. So, okay. So, yep, I know that it's a lot to digest, but I think if you go through it, maybe I'm wrong, maybe not, but the plot has a lot on it. It defines the profile likelihood. I guess I don't know if it says in here, but it should say that. Yeah, it doesn't actually say in here, does it? The Q mu, this Q mu is -2. Yeah, okay, there it is, -2 log of that thing, and then you have Q0 there, Q0 there, Q mu there, Q mu there. All your p-values and the different kinds of plots. And then this one, as you scan the mass, the thing that's being plotted is mu hat, right, which is this guy right here. So it's all kind of together on one slide, but there's still a lot going on. Okay.
The slide is taken from
I made this slide. This was sorry. Let me remember let me look at. You can date it from the p-value. So this was in December 2011. Yeah.
Well, this talking about what the expected hypothesis.
The dotted lines here. Yeah. So if this is the discovery picture, then I need to go over here to this one where Q0, because that 0 is telling me I'm testing the background only. Okay. And so what for the observed data. I had a certain mu hat, a certain value Q0. That's the red line here, and I get a p-value, and that's what gives me this, right? Maybe it doesn't match the plot in the sense that I should choose a different mass value or something. But the dotted line here, the expected means take the median of this signal plus background. So that's before you did the experiment. You knew what the distribution looks like. You take the median. It's a different value of this Q0 that you'd never observed, but that's your expected significance. Like that's saying if the Higgs is really at that mass with the expected signal rate, that your p-value is going to be really small, right? Or whatever value is being plotted. And similarly, what's happening here with the dotted curve here for the expected is you're imagining you're doing limits. So you take the expected value of b, the expected value of Q mu for the background only. And then and you're calculating what the upper limit would be for that thing. Okay. I know it's not super exciting, but it's there's a lot there. But this is the procedure that we're basically using. So, okay. So then, so I'm going to move on then. So I showed limits here. These are limits. And I'm going to talk about now sort of limits and confidence intervals. I'm just going to think about it a little bit more generally. Okay, so if you want, this was a one. Well, yeah, this gets funny later to think about this. We'll maybe come back to this plot, and I'll kind of maybe challenge your mind a little bit. But okay, let's go to this one. So here are plots. Okay, well, there we go. We see these kinds of plots all the time, right? And we need to make sure that we know how to interpret them, okay? And I think everyone sort of knows how to interpret them in the sense that they're like exclusion regions or something, but like more more, precisely what is the statement, right? Or these kinds of plots, right? These are all, exclusion parameter exclusion plots, right? And some of them are like, very complicated looking. So my question is, I just picked one, is what, what is this thing? You see it all the time. What does it mean? And I should probably take that away. You probably already read it. But yeah. So, what's your interpretation of, like, say, the blue dotted line? What does it mean? Like, what's the definition of that thing? Or, like, or maybe I don't want to, how would you interpret the blue dotted line? Okay, but, yeah, like 1 sigma contour, maybe means something that has to do with 68% of something.
Parameters outside are excluded and
Okay, yeah. So what? But then you need to tell me, what does the excluded at the 68% confidence level mean?
68% of the realization data, the true value would lie within the
Yeah. So that is what it means. That's right. So I think, but a lot of times, this is definitely also meant for some other people, but I think a lot of times people want to look at this plot and think it means that the true value of, say, the top mass and the W mass is inside of the dotted line with 68% probability, right? And would be great if that's what it means, but that kind of statement is, has the form probability of the theory given the data. The probability that the W mass and top mass are in the dotted line is blah, blah, 68%, right? Now, so the way that you can kind of avoid that is, remember, the top mass and W mass, depends on how you think about the world. The way I think of it, they have some true unknown value, and there's some point in that plane that's the true value, right? And if I redid the experiment, I'm going to get different data, and the dotted line is going to move around, right? So those contours are random. Different data, they're going to move around. So the 68% confidence level means that pick a spot in the plane that's the true value. It's actually not even a statement about the contour. It's a statement about the procedure that made the contour. The procedure that made the contour is such that it will cover the true value, that contour will cover the true value 68% of the time. And that should be true no matter what the true value is. So you should be able to pick any point in the plane. Imagine that's the true value. That's the thing that's generating the data. You do the experiment many, many times. Each time you apply some procedure to make a dotted line, and you ask, does it cover the true value or not? Sometimes it will, sometimes it won't, and 68% of the time it should, or you're doing something wrong. Yeah? Yeah, they're not the same statement, right? Because in this case, it could be that the true value is, over here. And if it's there, what's the probability that the true value is inside the contour? But 68%, but of the time means I do a bunch of different experiments, and I apply the procedure. The procedure makes a dotted line, and it's true that in 68% of those cases, the true value would be inside of the contour. But for this particular plot, it does not mean that the true value is inside the thing 68% of the time. And in this particular plot, it's either in it or not, right?
It sounds like semantics, no?
But it's exactly Bayes' theorem,
Can we say this way? It's 68% is the space of realization, the ensemble is the space of realization for a given data point, rather than 68% in the space of theory.
Yeah, in this plot, if you think of a particular point as being the true value, it's either in there or not, right? That's a 1 or a 0. So there's no probability to calculate, right? So that's what I mean. Like in Bayes' theorem, if you don't have a prior over top mass and W mass, then that's kind of a meaningless question, right? So you can talk about Bayesian credible intervals where you can make a contour that looks just like that. You make it through a different means, and now it's the probability that the parameter is inside of V is the dotted line, that particular region. I can calculate that with Bayes' theorem. I need the posterior of the parameter given my observation, and then I just integrate in V, and it's 68%. But this posterior is coming from here, right? And there's the likelihood piece, and then there's a prior, right? And if you don't have the prior, you just can't calculate that thing. if you have a prior, you can calculate it, and that's great, and go ahead. So the thing that's a little bit, that also gets to be a little bit weird is like how am I going to come up with a procedure that's going to be able to cover that's going to make contours that are going to cover the true value 68% of the time, no matter what the true value is, right? That doesn't sound like it's necessarily trivial, right? And so I can flip through, well, here's not my joke, but especially given like how unsatisfying that seems, right? So so there's this quote I like, Bayesians address the question that everyone is interested in by by using assumptions that no one believes, which is the prior here, right? I'm ruining the joke. Yeah, okay, I'm the joke. And frequentists use impeccable logic to deal with an issue of no interest to anyone. So that's kind of the case. So this is how it works, and I'm going to go through it kind of quickly. But what you do is you imagine all the different values of the parameter. You imagine the distribution of some quantity, which could be like the test statistic that we were talking about. So it's just a real valued quantity. And for all the different values, you're going to get a different distribution, right? And now I pick some way. Let's just concentrate on one of them, one value of theta. I'm going to choose one way of finding a region in the space of the data that has, say, 95% of the probability. So alpha is 5% here. This is 95% of the probability. There's lots of ways of doing it. This is like one in the middle. I could integrate from the left. I could integrate, make it balanced. I could integrate from whatever the right, etc. Lots of ways of doing it. Now I imagine these, all the different values of theta, and then I stitch them together, and I forget about the distributions, right? So now here's the space of the data. Here are the space of the parameters. This thing is called a confidence belt, okay? And then I make an observation, a particular value of x naught, and then I do the intersection through that, and I consider all the values of theta where the observed value is inside this confidence belt, okay? And then this region from theta minus to theta plus is how you define the confidence interval for this particular observation. If I got a different observation, it's going to bounce around. I'm going to get different intervals. So this is the procedure, okay? This is called the Nyman construction. And let's see if we have it here. So this is kind of the statement, which maybe makes it kind of clear. If you think about it, it will become obvious, but it's semantically kind of gets a little tough. But for no matter what the value of theta is, for every point theta, if that were the true value, then the data would fall in this green band. That's how we defined it, right? And if it falls in the green band, then then that value of theta is going to be in the confidence interval. So it works, right? So and it also does not mean that the Bayesian thing, right? Here's theta true. Imagine that's the true value. There's a chance the data falls over here, and that value of theta true is not inside the confidence belt. I mean, it's not inside the confidence interval. So that it can happen, right? You can make mistakes, but that's the whole point. Is you want to, 5% of the time that's going to happen. Okay, so that whole thing is called the Nyman construction, and this property of how often the procedure makes an interval that covers the true value is called coverage. Okay, it's covering the true value. Okay, and so if it's under coverage, that means that you're kind of you're being too optimistic and you're like underestimating your systematics or something like that. And if over coverage is like a conservative limit where people are wanting to cover their butts or something. Okay, all right. So this one is that okay? All right. So I think that hopefully you can go through and look at these slides, and maybe if you're a visual thinker, it's nice. Okay. And if you're not a visual thinker, the entire statement is this: that confidence interval is equal to the set of parameter points theta, such that the probability of whatever your test statistic that you choose, t of your whatever your data is bigger than some cutoff that you define. I see that is equal to this alpha. So alpha is like 5% or something like that. This is the distribution of my test statistic. I find the threshold that I need to make it be, in that plot. If this is t, here's my distribution, and then I go out some amount. This is what I'm calling k alpha. That probability right there is alpha. Okay, so that's this statement, right? And it's just the set of points theta where that thing is true. Okay, so that's the same as the Nyman construction. Okay. Okay, now, so now I want to just go back to something that's, since this is maybe nice in theory, but it's not like in practice probably what you're going to be doing very often. I want to touch base with something that you probably will do a lot in your life, okay? So going back to the logic a little bit, what we had is this quantity was like the thing that I was calling Q mu before, right? This is the -2 log of the profile likelihood ratio. And this Wilkes theorem over here is saying that if so that's the vertical axis, if the true value is the same value that you're testing, then that thing has a chi-square distribution, right? And so I know how far out to go on a chi-square distribution to get 5%, right? So that's just a table. In a lookup table, I find that number, right? Now what I can imagine is that this plot is being made for a particular value of theta, right? Okay, now pause. Now we're going to kind of turn sideways. This axis here is now the log likelihood ratio for my observed data, and I'm going to scan theta. And what do? I get a log likelihood curve. Just turn sideways, right? And so now we're going to just turn that whole thing sideways, forget about Wilkes theorem, and that's kind of where we started. This is what people do all the time, right? You get a log likelihood curve, you find the minimum of it, you go up by a certain amount, and then you call the region between, that threshold between here and here is your uncertainty, right? Like this is typically how people make error contours. They get the best fit value, and the error just comes from the region with delta chi-square bigger than a certain amount. But you see this all the time, but like, why do I care about how big that curve is, right? Like, why? Like, that seems like if I didn't tell you this story before, like, why would you be concerned about that, like that delta chi-square and the value of that curve, right? So the rationale is from this whole story that we were just telling, okay? So a lot of times you just don't bother with generating toys and everything. You just make this curve and you're done, okay? But that's where it comes from. Okay, and yeah, so you see these things all the time. Okay. I'm not going to go through these slides, but okay. So I'm going to flip through stuff. All of this is basically that life gets, well, maybe I'll say a little bit. Life gets more complicated when you have boundaries. If you don't have boundaries on your parameter, then everything looks like a chi-square, and it's this picture that I was just drawing with Wilkes theorem and chi-squares. When you have a boundary, it affects what's going on. And so then the how far you have to go to get 95% of the probability changes when you get close to the boundary. And this is the reason also why people do things like CLS and stuff like that. Okay, but I didn't want to spend too long there. But I will say that if I confine this plot again, here CLS is defined in this plot, and it's defined as P mu over 1 minus PB. So there's P mu, that the probability for your that you're using usually for making an upper limit, and then this P0 is the probability under the background only. Wrong one. This is 1 minus PB. Right here is that other probability, and that ratio is what people call CLS. Okay, and the reason that you do it is because it protects you from being able to set limits when you're not sensitive. And maybe I will say a little bit about that because it's important. Is that we can do a really simple example though. So let's say that we'll just even count events. Okay, say this is just the number of events that I observe, and this is the distribution that I expect for a background only. Right? Now, if I have an observation here, like let's imagine this is our observation, and I want to put an upper limit on the signal. What do? I consider signal plus background curves, like lots of different signal plus background curves. I keep going and keep going until I get one, like out here, that has something like 5% of the probability. Right? Any signal that's bigger than that is not consistent with the data and has this p-value that's less than 5%, so that would exclude it. So the magic value here, right, for the signal that I added, where this is 5%, is usually where your upper limit is. Okay, but now consider a situation let's consider the situation where the signal is just incredibly tiny. So I'll just use this dotted line that I did, where it's epsilon. Okay, so that experiment doesn't. I mean, you can just look at it. The signal plus background only look basically the same, right? This experiment does not have any sensitivity. You should not be able to exclude this epsilon amount of signal, right? Because the experiment is not sensitive. However, there is a point over here where this is 5%, right? And there's a 5% chance that your data, under the background-only scenario, happens to fall here, right? So you have a 5% chance of excluding arbitrarily small signals, right? Even if your experiment is not sensitive at all. And so there's nothing wrong logically. It obeys all the properties we wanted. It's just, as a physicist, we're not happy with that, right? And so people want to come up with a way to protect ourselves from excluding incredibly small signal values where you don't have sensitivity. And the way that you did that is, in this case, the probability under the background only is also very small, right? So that's this. So, so everything is kind of flipped around from how you would expect it, but CLS is basically protecting you from doing that, and it leads to over coverage. Okay, and so on average, the background only, this 1 minus PB is going to be 50%, right? So what would have been a 95% confidence interval turns into like a 97.5% confidence interval. So CLS over covers and is conservative, but it does so because it's trying to protect you against excluding arbitrarily small signals where you're not sensitive. So that's why people do it. But it is not a method. CLS is just a ratio of some probabilities. And you have to define everything else about how you calculate those probabilities. And so at the LHC, we're calculating the probabilities through this procedure that I'm talking about. And then at the end, you add this kind of afterburner of CLS to try to protect yourself. Okay. All right. So that was all of that kind of stuff that I wanted to get through. And then I had a couple of other little things that are a little bit more fun and exciting to end on, but I don't know where I am in terms of time. It's also late. So 5 minutes? Okay. So then we can either just do questions or we can stop. I could say, here's another little joke. You might, wonder why I'm down on Bayesians sometimes. So Archbishop Thomas Cranmer, he was born in 1489. He wrote the Book of Common Prayer in England, apparently. 2 centuries later, Thomas Bayes, you may or may not have known, was a nonconformist minister who refused to use Cranmer's book. So it's really all just like a long family feud. So I have various things about Bayesian stuff that we could talk about, Markov chain Monte Carlo. This part is maybe one of the things that we could mention is that we talked about, where do you get your priors from? And, it can either be subjective, like, your degree of belief, but there's also a whole class of priors that come from what are called formal rules, okay? So one of them is something called Jeffrey's prior, which is nice because it's actually invented by a physicist who became a very famous statistician. And so basically he says that you're going to have a prior that's defined as the square root of I, which is the Fisher information at the point theta. And we talked about the Fisher information before. And the nice thing about that is that you could go through this little derivation is that it's covariant to reparametrization of your theory. So if you think of the MSSM in terms of tangent beta, and then the aliens come and think of it in terms of then you can calculate the Jacobian transformation between it, and both people will agree. Okay. So it's nice in that way. So there's a way to come up with a prior that is in some sense objective. Okay. In terms of Bayesian things, these are quotes from famous Bayesians, okay? And basically, one of the things is, that you should try as much as possible to separate the objective likelihood part from the priors. If you're also doing it, you should try to investigate the sensitivity to different choices of priors. And the idea that flat priors and high dimensions are super dangerous, okay? So be careful. And if you say, I'm using a flat prior and it's uniform and I don't need to worry about it, but I'm doing a 19-dimensional PMSSM scan, think twice. And also just the, where is the, maybe it was on the previous one. But this point right here about performing, looking at the sensitivity, this is called sensitivity analysis. And there's a quote that basically says, sensitivity analysis is the heart of scientific Bayesianism. Okay, so So don't just say my prior is right. Try a few, communicate to the reader how sensitive you are, and that's the. There's also the look elsewhere effect. We could say a little bit. If people want to see a little bit about the. Okay, so and then I think we'll be able to end here, and we'll be able to talk about 750, and it'll be fun. So in this plot, this is supposed to be like the invariant mass, say, of some particle. Okay, you have a dotted line, which is like some background fit, and then you have a bump on top of it. You're scanning the location of the bump, right? This thing, as I scan the parameter m, which is my mass parameter, this qm is the same thing we talked about before, -2 log likelihood. Okay, and so it's some curve that's hopping around as I scan along the mass. And in this plot, it doesn't really look like it, but there's a little bit of an excess of events there, so you get the curve goes up, there. Now, the thing is that if some all-powerful person told you what the true mass of the particle was, then you would know where to look, and the distribution of this qm, if the background only is true, would be this chi-square type of quantity, right? And you'd be able to calculate the p-values and the significance. But if you don't know where to look, you have lots of chances to see an excess, right? So intuitively, the look elsewhere effect is just the number of places. You looked in a bunch of places, you had a whole bunch of chances to see something. And another way of saying it is you're testing the same background-only hypothesis, right? If you're testing the same background-only hypothesis many, many times, and they're all independent from each other, you have a whole bunch of chances to falsely exclude it, right? So you have a bunch of chances to make a mistake. So you need to correct for that. And that's that's what the look elsewhere effect is. If you these aren't all independent from each other, though, right? It's a continuous parameter, and 2 points that are close to each other are highly correlated. So what you can do, though, is you can think of this m, as some parameter, and this thing, if I imagine doing the experiment over and over again, if the background only was true, this is a chi-square random field, okay? It's just like the CMB sky is a Gaussian random field, right? At every point in the CMB sky, the temperature that you see, it's some random, it's drawn out of a random Gaussian, but it and the point right next to it are correlated to each other. So, if I basically just took the square root of this thing, it would be a Gaussian random field, just like a one-dimensional CMB sky. And so because of that, you sort of know how it behaves, and you can figure out what is the chance, like if this is the biggest peak, what's the chance that I saw a peak that big anywhere along there, okay? And there's some theory for being able to figure that out, as described by some physicists in this paper, and it's related to some more fundamental stuff from some statisticians in the 70s and 80s, and basically says that you take your local p-value, which means like the p-value naively assuming chi-square distributions and everything at the biggest point, okay? So like I knew where to look, no look elsewhere effect, that's the local p-value, and you add to it some correction, okay? And the correction, this is how it works. You need to say sorry. So yeah, it gets a little bit funky. So Q ref here is basically, you can think of it as like the value of Q at the peak, okay? The value that you're testing. So the thing that say looked like it was 5 sigma before correcting for the look elsewhere effect. And then Q test is some other lower value. You just pick, it's random, it's arbitrary, you just pick a number. And what you do here, this means the expected number of up crossings, that's what n is how many times did this curve go up above this reference value. Okay, so you look at it and you see how many times it ticks up above there. And the expected number of up crossings is some number, and then you know the value that you're testing, the value that was this reference, and you have this this exponential, and this is the correction that you apply. And intuitively, what it's saying is that if I have a very good mass resolution, then I would expect I have lots of bumps, right? And the number of places that I looked is roughly the mass range divided by the mass resolution, right? And if that's the case, then this thing is going to hop up and down a lot, and this number is going to be big. You're going to have a lot of up crossings. If I have really crappy mass resolution, then it's not going to fluctuate a lot. I'm only going to have like 1 or 2 up crossings, and this number is going to be small, and the correction is going to be small. Okay, but then there's this other piece so this first part is kind of what you would expect from mass range divided by mass resolution. This part is not expected, And basically what it's saying is that the look elsewhere effect gets bigger the more significant your observation is. So, which is kind of surprising, okay? And one way of thinking of it is that if you have a really big excess, there are a whole bunch of events there, and so your kind of mass resolution is kind of getting better in some sense. Like you would be able to resolve the mass better if there's a really big peak than if there was not a very big peak. So there's a few different ways to interpret this thing, but this part was not appreciated by particle physicists until recently. And so this is the way that we're correcting for the look elsewhere effect, from the Higgs on. Now this one, in this case, only had one parameter that we were scanning, right? We were testing that, and that parameter, that mass parameter, doesn't mean anything in the background only case, right? Like what's the, the shape is the same for the background only no matter what the mass of the particle is, right? So in the case of 750, now it's a two-dimensional problem. You have the mass of, x, and you also have the width, okay? And so you need to figure out how to correct for that. It turns out that the same theory gets generalized, and this stuff is kind of crazy, but what you do is this scan right here is the equivalent, is a two-dimensional version of this plot, right? So this had one parameter, and this axis was the log likelihood. Here, coming out of the board is the log likelihood, and these two parameters are what I'm scanning over. And what you do now is instead of calculating the number of up crossings, the number of up crossings, you had a reference level here. You still do a reference level, okay? So you pick some reference level, that's called mu here, and then you think of what the little contours of that thing look like, okay? And then what's somewhat surprising is you calculate the expected value of the Euler characteristic of those contours. Okay, sure, why not? And then so A mu is the set are those contours, and then the expected value of the Euler characteristic of those excursion sets is equal to this formula, which looks a lot like the one we had before, the local p-value plus e to the minus whatever with this was like the expected number of up crossings, but now there's another term for the 2D one, and you can calculate these coefficients, and then you can correct for the 2D look elsewhere effect. So the reason that these plots are being made for 750 is because we're correcting for the 2D look elsewhere effect, not just because they're pretty. Okay, so this is how we do it. I have some code to do that. You can do it on the sky, for instance, if you want to know like what's the chance that that some flash of light happened to align with a gravitational, two black holes merging or something. You would have a look elsewhere effect that you could correct for. There's also the issue that's happening now that you have Atlas and CMS seeing this bump, and you would how do you deal with the look elsewhere effect? Can you say that Atlas told you where to go look for, in CMS, and then you don't have to correct or not, right? So I have a little, thing about that, and basically you can tell that there should be some permutation symmetry between Atlas and CMS there. The idea that Atlas is going to tell you where to go look on CMS breaks that, and that's clearly not the right way to do it. So this thing that has a link there basically tells you the right way to do it, which is to combine and then correct for the look elsewhere effect once. But then there's also some nice things about you can, in this picture, you can do things pretty fast, and I come up with some way of correcting for the look elsewhere effect of two experiments. And that's what's being done here. There's search 1, search 2. Each one of them has their own, log likelihood curves, and then you get to the combined one, and I can predict what the look elsewhere effect of the combination is. And this is the prediction, and then this is the, running a bunch of toy simulations. And all these predictions only work when it's a significant bump, and so it works very well when it's significant, and it doesn't work well when it's not significant. So at your own time, if you want, you can look into that and think about how to deal with two experiments, and then this stuff I won't go into. So, okay, I'm done. Yeah, I'm done. Okay, yeah, thank you. Okay, so there, yeah.
Did you ever just for fun make a version of that plot where there's this kind of the x-axis?
What's that?
Did you ever make a version of this plot with the combined significance?
Oh. I did internally. I didn't do it for because it got a little bit sensitive for reasons that we can talk about later.
Do you remember the number on the y-axis?
Yeah, I mean, yeah. For instance, it turns out that in the case of the Atlas and CMS, the whole, because they're both kind of similar in sensitivity, and they both have roughly the same observed significance, that the idea of one tells you where to look and the other one is not, is numerically pretty close. It's just that, more generally that might not work out so well. Okay. So I know I ended, but I want to say again, thank you very much. I really appreciated everything and all the feedback and enthusiasm, and enjoy your weekend and all that stuff, and enjoy the rest of Tazi. And yeah, it's been nice meeting you and hanging out. Okay, take care. Hey.
A quick question,
Yeah.
because I think you answered me, but I didn't understand.
Yeah.
So, and then, can you take the mean or the medium and it's the same?
Oh, the two numbers are different. So you just need to, but then you need to say, what do you mean when you say expected?
No, but I mean, if in the end, if you did 1,000 Monte Carlos, you would convert to something, to some curve that you would have gotten if you had taken the median or